So the pathways that will reduce CO2 emissions are not new to us. These decarbonization options include demand-side measures, which lower the demand for primary resources by increasing circularity, increasing energy efficiency by adopting production equipment that will reduce the energy use per product volume, replacing fossil fuels for heating with renewable electricity via electrification, and replacing feedstocks of fuels with carbon-neutral hydrogen or sustainably produced biomass. Now, capturing carbon for storage or utilization is the focus of this webinar, and there is immense potential for CO2 emissions to be reduced by deploying CCUS technologies in these various sectors. So in the fuel transformation sector, we see a potential reduction of 86%. If CCUS technologies are deployed in cement, 47, chemicals, 10%, iron and steel is 4%, and your power generation is 3% potential reduction of CO2 emissions. So we further see that the gigaton of CO2 that is captured per year will continue to grow. So the total GHG emissions in 2020 amounted to 56 gigatons of CO2 equivalent, with CO2 itself accounting for 75% of the total GHG emissions. While this number was high, the global CO2 emissions actually reduced by 5.2% due to the impacts that COVID-19 had on energy demand. So carbon dioxide, it generally originates from numerous sources like large-scale intensive industrial practices, such as power production, iron and steel, cement industries, and fossil fuel combustion. And fossil fuel combustion is considered one of the largest sources of CO2 emissions. Now, what happened was that the rapid global economic recovery that followed COVID-19 resulted in a 6% increase from 2020 values of CO2 emissions from energy combustion and industrial processes. And this resulted in a combined total of 36.3 gigatons of CO2 emissions, of which 35% was from the transportation sector and 30% was from the industrial processes in 2021. So it is clear that CO2 is still a problem, and the cost of damage from a ton of CO2 emissions amounted to $31.5 per ton. And we also measured that in May of 2022, the global average concentration of CO2 that was recorded was 421 parts per million, which was a new high. From all this information, we're also estimating that there will be a 200% increase in carbon tax by 2030. So clearly, we need alternative pathways to turn the CO2 from a liability into an asset. So your CCU technologies can sequester CO2 for diverse time scale periods depending on the usage of the final product. For instance, the enhanced oil recovery and mineralization routes are considered long-term permanent sequestration options, which can store CO2 for decades, while other CCU routes offer a more short-term sequestration. Systems that are based on CCU actually complement the CCS routes, but they provide additional benefits. However, it is not actually an alternative to your CCS because of its low sequestered amounts compared to the storage option and the large quantities of CO2 that still need to be offset to meet the climate change targets. But benefits can include the reuse of a once considered waste to become an alternative resource to fossil fuels. CCU also provides significant economic incentives for business actors who can then diversify their revenue portfolios by benefiting from additional and new industrial practices that utilize the CO2 or by selling the captured CO2 to other interested users. While CCS has a more considerable CO2 mitigation potential, the additional opportunities that CCU offers are worth exploring, mainly since many products have emerged as potential sinks for CO2. So, what are these different pathways to utilize CO2? We are going to be focusing on e-fuels, enhanced oil recovery, construction materials, food and beverage, and energy storage. So let's get started. The first pathway is your CO2 utilization for e-fuels. So the conversion of CO2 to fuels delivers many benefits to the energy sector, including the elimination of CO2 emanating from your power and industrial sectors, the additional generation of fuels through sustainable processes, and the reduction of fossil fuel consumption in the generation of fuels. Now, the production of e-fuels is done from renewable power, and this renewable power is also used for electrolysis and the production of the green hydrogen. So captured CO2 from sustainable sources is then included and mixed with the green hydrogen. It is then converted into fuels using various technologies. Here, the Fischer-Tropsch conversion process is shown, which converts CO2 and H2 into hydrocarbon fuels. These e-fuels can be used in various applications like automobiles, marine transport, or aviation fuels. These e-fuels also have advantages as they can directly replace the conventional fuel as existing infrastructure and power units can be used. It has a higher quality than fossil fuels as a pure feedstock that does not have a sulfur content is used. It also has good stationary storability and existing fleets can be operated in a climate neutral way. The only disadvantage is that it is more expensive than the fossil fuel process because of the high cost of the hydrogen production. So let's go a bit deeper into the conversion technology. So I have explained how Fischer-Tropsch works in the previous slide. It is used to produce e-jet fuels, e-diesel, and e-petrol. It does require the presence of these metal catalysts, and the optimum temperatures are about 150 to 300 degrees Celsius. And pressures, they vary from 1 to several tens of atmospheres. So in electrochemical conversion of carbon dioxide, it is used to produce fuels by converting CO2 first to syngas with the addition of H2, and then to an organic feedstock of fuels in a syngas reactor. So the electrochemical conversion of CO2 has been rapidly expanding, and the process converts CO2 into products such as syngas, your e-methane, e-methanol, or e-diesel, using the renewable energy and the renewable hydrogen. So your catalytic conversion employs an alkaline electrolyzer and excess renewable energy for converting CO2 through a catalytic exothermic reaction. Your catalytic conversion of CO2 involves the production of e-methanol, e-petrol, or e-jet fuel via thermal catalytic CO2 hydrogenation.